So welcome. Today we're going to be talking about fuel cells and hybrid energy. The first topic that we're going to talk about is driving efficiency. And as you look at a network, one of the things that operators are doing and equipment vendors are doing is trying to improve the efficiency of their network. So as you look at a hybrid energy solution, the first thing you want to do is how to improve the efficiency. So that might be upgrading to next generation electronics. It might be upgrading the rectifier plant to something that's more efficient. And in the end, it's been shown by various research by Ericsson and others that you can save up to probably 70% of the total energy consumption at a site can be saved by just changing the technology, upgrading and improving the technology. So as you look at a hybrid model, if I can implement a solution that's 70% smaller than I did last year or 2 years ago or 3 years ago, the cost improvements are significant, and that's one of the first steps you should do. A telecom power system is made up of several components, and this illustrates the various devices that could be used to power the network. And the traditional model would be the utility grid feeding in through a rectifier system to feed the DC load. So directly through this model to the equipment load and supplied with a diesel backup generator. That model is used world over and is very capable to provide all the power needs. However, as you look at sites that have grid problems, grid stability problems, or maybe no grid, then you start to look at how do I hybridize the system. So you start to look at maybe the addition of a PV, a solar solution, wind, and in the case of what I'm talking about today, primarily would be fuel cells. To add that in as a generator device that can provide assured energy to your load at any given time. Obviously, batteries are a component in all of this. You need to have storage system, and whether you're running a diesel generator with batteries in a charge-discharge model, or you're running with some of the hybrid models, off-grid solar, wind, you still need the storage component there all the time. It's how you balance and how you manage that and how you actually put an intelligent layer on top of that to support what your end goal needs to be in meeting your cost objectives and your power objectives. So I'm going to talk about each of the components briefly here. So the most common solar solution would be a photovoltaic array, widely used around the globe, both in residential, commercial, as well as telecommunications. Capital cost is relatively high, but it's been coming down fairly rapidly in the last couple of years. PV manufacturing costs have come way down, and today there's a little bit of a surplus in supply versus demand. Physical space is a big issue. You have to actually plan for the physical space that's necessary to provide the output power that you need to provide your site. That could range from systems that are as small as this that might be 10 or 12 foot square to very large systems that have multiple kilowatts that have to provide maybe 50 or 60 feet of space at a site to provide enough power. So there is a site consideration. One of the most critical things to consider is that it's intermittent power. You have to have something else to support it. You can't provide typically 100% power with a PV array. And even if you can, you still need to do it as a charge model and a discharge model with batteries. Obviously, it's not effective and efficient at all latitudes. In the northern climates, northern latitudes, southern latitudes, it's not as efficient to use solar just because of where the angle of the sun and the amount of sun you're going to get during the year. Wind, most common is small wind that people are using, and typically it's a DC output of the wind turbine. And there's solutions that both are vertical axis is shown here and horizontal axis that is shown here for, you might be concerned about vibration or how the mounting structure works. So there's different types of that. Capital cost is similar, moderate to high in the cost per kilowatt or cost per watt. Again, intermittent power, the wind does not blow all the time, so you need to have something else there to ensure that there's power and survivability of the network. Sometimes there's installation restrictions, and this can be true with all these solutions, whether it's even your radio cabinet would have restrictions. But in wind, you might have restrictions to put two towers next to each other or to put a tower top wind turbine on top of an existing structure due to the actual true structural loads of it. So you've got to be concerned about that. Certainly clean and renewable. There's once it's installed, it's actually has no real cost of operations other than maintenance on the wind turbine. Fuel cells, most commonly used in this technology is proton exchange membranes. It's an electrochemical cell similar to a battery, but it produces electricity continuous as long as there's fuel, where a battery, being an electrochemical cell, once the charge is depleted, there is nothing left for it. You have to recharge it with something to be able to reuse it, where the fuel cell can work autonomously with fuel. So they can be mounted in a variety of different ways. Capital cost is moderate, so very similar to the wind turbine in terms of cost per watt. A very high reliability, low maintenance solution, so they can be added onto a site with very little concern for adding reliability and maintenance concerns. Environmentally, at point of use, they're very clean and safe. There's no emissions. They are exempt from things like the CARB requirements in California because there's no emissions. The hydrogen itself is typically derived from natural gas, so there is, if you go back to the production of it, there's still a carbon footprint, but it's certainly much less than burning fuel in an internal combustion engine. Fuel logistics around the world vary quite a bit, so that's one of the areas of consideration that must be given to look at using fuel cells at these sites. And these photographs, we show both solutions that can be exchanged by removing and adding cylinders, or solutions that can actually be refilled on site using a trailer. Telecom batteries. The design of a telecom battery has been fairly consistent for many years. Most commonly in the outside plant environment is a valve-regulated lead-acid battery. There are new chemistries that are coming online as people are starting to say, well, I want more energy density and a smaller footprint, so there are people looking at NiCads and lithium ions and other technologies in that, but most frequently used are valve-regulated batteries. Cost is probably the lowest, but the restriction you face with a battery, again, is that once the charge is depleted, you have nothing left. So in a poor grid solution, once I've depleted that battery, if I can't bring a portable genset out or there's some other source of energy to recharge the battery, my site goes down. So that's one of the drawbacks. Life expectancy is another one. A traditional battery, unless it's got a conditioned environment, is going to last maybe 3 years, 4 years, 5 years, but not much beyond that. In conditioned environments, it might be 5 to 7 years, but we've seen cases as low as 18 months for replacement of batteries in high temperature climates. Environmentally, there's a little bit of concern. Most battery manufacturers have actually implemented return logistics or reverse logistics to recycle those batteries, but that's an important thing that must be considered using it because it's hazardous waste. On the genset side, most common is going to be diesel, probably second is propane, and there's some natural gas gensets that are used in some parts of the world where piped natural gas exists. They can be portable. A lot of people use trailer mounted gensets, which makes it easy to take out to a site that needs to have additional power. Capital, again, is typically low or lower than others. Long run time, these things will last a long time, and they'll last as long as you have fuel. So like a fuel cell, as long as you have fuel, the genset will continue to operate. But they do have a significant amount more maintenance required with filter and fuel storage issues, oil changes and things like that must be taken care of and done on a regular basis. One of the most important things, again, that face many of this is environmental. So now you've got emissions, you've got spillage. It's not uncommon to have people have to do a lot of paperwork just to show I comply with spillage requirements, not even reporting spillage, just to report the compliance. Most of these gensets are AC devices. This being an exception, this is a DC generator here. But if it's an AC genset, it needs to have a transfer switch so you don't back power the grid, therefore causing a safety hazard to someone else at the grid site. The big issue that around the world really comes down to fuel theft. And actually in some cases the generator itself is being stolen. But fuel theft is a big issue. In some cases in developing countries, it's between 30 and 50% of the fuel is being stolen at the sites. So if I only get 50% of my capacity and I've got some that's high maintenance, well, maybe it's time to look at a different solution. So a complicated slide here in this flow chart, but basically this goes through a decision tree matrix of looking at a hybrid power. And it's a simple thing. Do I have grid power, yes or no? If I don't, well, it starts to drive a set of decisions. If I do have grid power, it starts to drive a different set of decisions. And in the end, inside of the green box, it basically says you go through then and evaluate your various devices, but based on the site needs, the environmental consideration, your total cost of ownership model, and put it into this and come up with a site solution. This can be fairly automated based on certain conditions that exist at each site or within a certain company, so that they say, well, my decision's always X if these conditions are met. But in the end, it basically says that if, in some cases I might have a policy on corporate sustainability. Well, if that's true, then maybe I don't want to have an emissions device. I want to have something that's green. Or if there's regulatory restrictions to an internal combustion generator, if the local municipal government says, I can't deploy this, well, then you choose something else. And this allows you to make those decisions through the process. These are just some of the examples of hybrid models where the amount of power is coming from various sources. So in this case, solar and wind, being the yellow and orange, provide most of the power most of the year, and the fuel cell in this case would be used to fill in a gap. The problem with wind and solar, to get 100% coverage sometimes means you add a significant amount more capital to that site. So the fuel cell can be used in as a finite gap fill, and that's true with a solar primary and with batteries and a fuel cell to fill in the gaps. This example is one we do with a US government customer that to add that last 10 to 15% of energy on an annual basis would have cost them 3 times the cost per site to do it with solar. So it changes dramatically to get that last few percent, where the fuel cell, it's going to work and it can fill in that gap and keep your solar array much smaller. Same thing of the other models. There are multiple incentives and resources available to help in hybrid energy. This is used for the US market primarily. Solar and wind has tax credits. Fuel cells have tax credits that are available based on a investment cost or a cost per kilowatt basis. Department of Energy has many resources available as well to use for determining the applicability of these technologies at a site. And then there's a website that's sponsored by a university that actually allows you to go in state by state and at the federal level and look at all the available alternate energy credits and programs that are available to an end user. And thank you.